Okay, good morning. Thanks to the organizers, especially Marcos, for giving me the opportunity to talk at this occasion. So the talk title is maybe a little bit scary. So I'll try to make it light at the beginning, and then there will be some mathematics at the end. And to make it lighter, I will tell you a story which takes place at approximately 700 kilometers from here, but at two different locations. So the first location is up there, just above our heads. It's a low altitude orbit satellite, which is one of the satellites of the Pleiad constellation. And that's the motivation behind the work I will be presenting. The other point, which is approximately 700 kilometers from here, is Toulouse, the city where I come from. So you may know that my lab in Toulouse, it's called LAAS, L-A-A-S. It stands for Laboratory of Analysis and Architecture of Systems. It's pretty general. It's a big lab of TENORS, the French National Institute for Scientific Research. And originally, in the 60s, in the end of the 60s, it was called Laboratoire d'automatique de ces applications spatiales, so the same acronyms, but different meaning, Laboratory of Automatic Control and Space Applications. And so if you come to LAAS, you'll notice that it's a quite extensive lab, 700 people approximately, on a quite extensive scientific campus in the south of Toulouse, next to a huge campus, which is the CNES campus, the French Space Agency campus. And so that's the picture you have here. That's the main entrance, the main gate of CNES, the French Space Agency. And in Toulouse, this is where they monitor activities of satellites and also the launchers, of the Ariane launchers. And not too far from CNES, there are premises of, now it's called Airbus, formerly Astrium, which is the place where they designed these satellites, the Pleiad satellites. And I checked yesterday, actually, this particular satellite, it's a twin satellite, two satellites. They were launched in 2011 and 12. And they were also partly manufactured in Friedrichshafen, which is just across the lake. So, nice coincidence. And these are Earth observation satellites equipped with very high resolution optics. And so they are in an orbit which is approximately 700 kilometers above our heads, which is sun-synchronous, which means that every day, at the same time, it passes above your head. And the reason it's the choice for this orbit is that it gives optimal lighting conditions to do photography. And so these orbits are revolving around the Earth for now about 12 years, 13 years. And so here is one. The other one is the same. And they are equipped with so many sensors that to deal with this sensor, to have a human just operating the amount of data is not manageable. So here I'm speaking about the sensors that monitor the satellite's health. I'm not speaking about processing of the data of the images which are taken, but just the health of the satellite, whether the instruments embarked are working well or not. And so the satellites send a lot of data to the CNES offices in Toulouse. And so this high volume stream of telemetry data must be processed. And since there are too many data, it must be partly automatized. So the goal is to at least partly, if not totally, automate the monitoring of satellite, the surveillance of satellite telemetry, with the objective of detecting potential problems early enough to ensure continuity of the missions. And what is implemented in these satellites, which are 12-year, 13-year-old, are basic thresholds, alarm thresholds on signals. And as soon as the signal goes over these thresholds, an alarm rings. And as you can see from this picture, which is real data from satellites, a signal could be anomalous. There could be an anomaly in the signal without the threshold being overpassed. And these thresholds, they may fail to capture deviations or drifts in the signals that could be precursors of failures in the system, in the satellite. So here you see we have this phenomenon here, which is below and above the threshold, but still there is something going wrong on the instrument. And eventually, this could lead to interruption of the mission. And so the motivation of this work is to provide a method to detect these anomalies. And there are many ways to do so, but in the project we have been involved in, we'll use a particular tool, some of which are already familiar with, but I don't expect everybody knows about it, and so I will introduce it as slowly as possible. This is the Christoffel Darboux kernel. Okay, so that's a very good introduction to the topic. Recently written book by colleagues, so Jean-Bernard Lasserre, who is in my lab in Toulouse, Edouard Powells, who is at Toulouse School of Economics, in the mathematics department, and Mihail Putina, who is at the University of California at Santa Barbara. And so it was published a few years ago, and you see the title. It's the application of the Christoffel Darboux kernel for data analysis. And so my talk will be about this particular object, and how can it be adapted to the need of anomaly detection and processing of signals like the ones we can find on satellites. So you see the cover picture of this book, two letters, clouds of points. So clouds of points, this is the data. And you see also a curve, well, two curves in red, which are actually level sets of a function. And you see that the level sets match closely the cloud of points. So we'll try to explain that. So now a little bit of mathematics. So I'm given a probability measure mu on a compact set K of Euclidean space Rn. And I attached an inner product to it and a norm. And so this makes, this provides me with the Hilbert space structure. And so I will denote P1, Pm, the orthonormal, non-orthonormal polynomial basis, not necessarily unique, for the finite dimensional vector space of polynomials in the Hilbert space, which are of degree up to d in n variables. Okay, so the dimension of this vector space is denoted by small m, and this is this binomial coefficient, n plus d choose n. And so once we have this, the Christoffel Darboux polynomial is just the sum of the squares of the orthonormal polynomials. So you give me mu, and I can construct by the Gram-Schmidt orthonormalization process the Christoffel Darboux polynomial as the sum of squares of the orthonormal polynomials with respect to mu. Another way to think about it is that if you have the matrix of moments of mu in some basis, any basis, then the polynomial can be understood as a quadratic form whose Gram matrix here in the middle, is inverse of the moment matrix, provided this matrix is invertible. If it's not invertible, we check a pseudo-inverse. So here I use a basis, but as you see from this, the polynomial itself does not depend on the basis. Okay? But if you have a moment matrix, usually you have it in some basis, and you can get the polynomial just by this operation. And actually, this is the orthonormalization process inversion of the matrix. By inversion, I mean that you just compute the eigenstructure and take the reciprocal of the eigenvalues. Okay? So this is one possible way to think of it. So it's some data which encodes information on a distribution of a mass that encodes a measure. Okay? That's also a motivation behind this notation, mu. So it's attached to mu. And it depends on the dimension, because, well, of course, it depends on the number of variables through its argument. X is a vector of Rn. Bless you. But it depends on D in the sense that the number of polynomials here that you sum up is a function of D, right? The larger the D, the more squares you have, and you see since this is a sum of squares, you add terms, so it's a nested family in some sense of polynomials, indexed by degree D. And we'll see that this dependence on D will be exploited a lot, especially when we let D go to infinity. We'll try to find out what happens with this object. Okay, another way to think about this Christoffel Darboux polynomial is via its variational characterization. So it's a solution of an optimization problem. It's a convex optimization problem, and there are two ways to think about it. The first expression is an operator norm. So you take the point evaluation, so the evaluation of P at a given point X, so X here is given. You square it, and you divide by the L2 norm of P respect to mu. This is a function of the polynomial, and then you take the maximum of all polynomial in the finite dimensional vector space. This number is now a function of X, and this is the value of the polynomial. This is not too hard to prove. It's in the book that I mentioned, but it's a few lines of calculations. It's not complicated. Another way, which is equivalent to think about it, is that this is the reciprocal, so 1 over a function, which is called the Christoffel function. So Christoffel Darboux polynomial, when you take the reciprocal, you have a rational function, and it is called the Christoffel function. And this Christoffel function is maybe even easier to interpret, in the sense that if you normalize the point evaluation of P at X, if you say that P of X is equal to 1, then the Christoffel function is just the minimum possible norm, the minimum possible L2 norm you can achieve with respect to all polynomials of degree up to D. So it's not difficult to prove that the average value of the Christoffel Darboux polynomial, so the integral of the polynomial against the measure to which it is attached, is actually the dimension of the vector space. M is this binomial coefficient. It's the dimension of this capital P, D, N vector space. So that's the value you should expect when you evaluate the polynomial in the support of the measure. That's the average value. And you can say more. You can construct concentration inequalities in the sense that the deviation around this average value decays very quickly as a function of epsilon here. So that's a typical concentration inequality, which says that most of the mass of the measure is concentrated into sublevel sets of the polynomial of value m, around the average value. So that if you look at the average value of this polynomial, you get a good idea of where the measure is supported. And this is how it is used for data analysis. If you have a cloud of points or a measure, you construct this object, and you look at its average value, sublevel set. So here is an example of a measure, which is the uniform measure on -1, 1. And what I did is that I took orthonormal polynomials with respect to this uniform measure. So this is in the previous slide. These are called Legendre polynomials. And I just take successive Legendre polynomials of increasing degrees, and I sum the squares of them. And for each degree, I get a polynomial that I represent here in color, you see. So these are low degree, and then I increase degree up to 30. This is a polynomial, so in terms of the degree, it grows polynomially. So I take the log to have moderate values here. And you see that the degree 30 sum of squares of Legendre polynomials is very large outside of the support of the measure. And it is as small as the sum of squares of polynomials can be inside the support. It cannot be smaller because the sum of squares of non-zero polynomials are normalized. And the average value actually is the dimension of the polynomial understood as a quadratic form. So here you are in one variable, so it's just a degree. So this average value here should be around 30 because it's the degree 30 sum of squares of Legendre polynomial. And you see that when you take this orange degree 30 Legendre polynomial and you take its sublevel sets at its average value, which is the set of points for which the polynomial are less than 30, and you get a pretty good approximation of the unit interval where the measure lives. Okay? So this is in one variable, and here is in two variables what we can get. So I took a cloud of points which has a moon shape, and I constructed from this cloud of points the empirical moment matrix, so the sum of Dirac measures with uniform weights at these points. And I computed by eigenvalue decomposition of the empirical moment matrix the Christoffel Darboux polynomial. So it's just linear algebra computation. And then in color here, from dark blue to yellow, I represent a graph in logarithmic scale of the Christoffel Darboux polynomial. And here you see it's just a quadratic, so it cannot do much. But you see that already it takes smaller value near points which are in the cloud, in the red cloud. And if I increase the degree, you see that the geometry adapts to the geometry of the cloud of points. You see degree 10 already very sharp increase of the polynomial outside the support of the measure, outside the moon, and moderate value of the polynomial inside the moon. This moderate value, on average, is the dimension of the polynomial. Okay, so now I can explain the cover picture of the book. Bernard, you have a question?
Degree is 20.
And I think that I took 10 here. It's degree 10, so it's...
Because you were showing degree 2, but
well,
this is not the quadratic.
well, it's in logarithmic scale, so I'm not sure how it looks like. I should
It's not the square.
I'm not sure. It may happen that it's the degree of the basis or the degree of the polynomial. I don't remember. No, indeed. We can check that offline. But you're concerned because this is not what a parabola would look like, right? Yeah. Well, it's in log scale, so I don't know too much how parabolas look in log scales. But yeah, maybe you're right. Yeah, you can check that out. But anyway, we are interested in large degree behavior. Of course, we should be careful not to use huge degrees because still there is this eigenstructure computation to be done. You must have the moment matrix and you must have its eigenvalues. You must have and to take the inverse. Well, if you want to know more about how these objects are manipulated, there is this book. And on the cover, you remember there is this CD. So C stands for Christoffel, D for Darboux. And so the authors just sampled points in shapes which resemble the letters. And they constructed a Christoffel Darboux polynomial of a certain degree. And they represented its average value, level set in red, which means that inside this red curve, most of the mass of the measure lies. Okay, so this is Erwin Christoffel, who at the end of his career was a professor in Strasbourg, but at the time Strasbourg was in Germany, early 20th century. And this is Gaston Darboux, who was in Paris. And there is one of the amphitheaters of the Henri Poincaré Institute in Paris, which is named to Darboux. I think the other one is Hermite, if I remember correctly. And, well, I'm not sure they met, but most likely they did at the International Congress of Mathematics before the 20th century. But I mean, we should ask historians of mathematics. At least they never worked directly together, but their names is attached to these objects. Okay, so that's the end of the part of the talk on the Christoffel Darboux polynomial. And the next part will be to try to pass from finite dimensions, so there are a cloud of points, to infinite dimensions where the points are functions. So from finite to infinite dimension. Other questions in the meantime?
Why are these polynomials named after Christoffel and?
Yeah, because it's related to. Thanks for asking. Indeed, maybe it's a good time to explain a little bit the background. So these are objects which are used in function approximation and approximation theory, and so they were interested in the best approximation of a function using only polynomials, or only just rational functions. And these objects naturally arise when solving these approximation problems. And this is where actually most of the properties and techniques are taken from. More recently, it's heavily used in machine learning, which is basically data analysis. And so there are a lot of techniques which are based on kernels. Christoffel Darboux kernels are just one of the possible kernels. There are many others. And I should also mention that even more recently, a certain number of people realized that these kernels could be useful to study convergence properties of the moment sum of squares hierarchy, which is a family of convex optimization problem constructed to solve non-convex optimization problems. So the speed of convergence of the moment sum of squares hierarchy can be studied with these objects as well. So if you want to know more, really, this book, I think, is a very good starting point. Especially the beginning is very introductory. It starts with the univariate case and the history. And this part was written by Mihai. And then it goes to the multivariate case and the application in data analysis, but also polynomial optimization. Other questions, Bernard?
So what happens when you have
When you have a curve, yeah, that's a good question. So, so far I spoke only of clouds of points, and so if you have enough points, the moment matrix is invertible. Just as soon as the size of the matrix is bigger than the number of samples and the samples are distinct, you have invertibility. If the matrix, if the measure is supported on a curve, then it depends on the nature of the curve. If the curve is algebraic, that means that there is a polynomial that vanishes on the support of the measure, in which case it will be seen in the null space of the moment matrix. So it means that the moment matrix won't be invertible. Okay, so if you have several polynomials that vanish on the support of mu, they will just show up in a null space of sufficiently large moment matrices. Okay? So if you look at the rank of the moment matrix as a function of the degree, it will, if the degree is large enough, it will vary like the Hilbert function as a polynomial whose degree is a dimension of the algebraic variety where all the polynomials vanish. Okay? So then the strategy, if you want to still deal with this object, is just to extract the polynomials from the null space. And what remains is an invertible matrix which contains the non-algebraic part of the support. So in particular, if the curve you're asking about is transcendental, so there is no polynomial that vanish on it, then the moment matrix will be invertible. And indeed, you can retrieve approximately the curve from the Christoffel Darboux polynomial, and by retrieve approximately, should be a little bit careful. Suppose that the curve is a graph of a function. Then you can approximate the graph from the Christoffel Darboux kernel with convergence guarantees. And with joint work with Edouard, also Swan, Marx, Tillman-Weisser, and Jean-Bernard Lasserre, we proved that we can do that with L1 convergence guarantees on compact sets. And L1 is the best you can hope for unless you have regularity of the graph. If the graph is just measurable, L1 is the best you can hope for. If I think that we also prove that if the graph is Lipschitz, we have Lipschitz convergence. Now, if you don't have a graph, it's a little bit more complicated, but basically it should be similar. I don't believe it has been done, but what is in the book is Hausdorff convergence proofs of the sublevel sets of the Christoffel Darboux polynomial to the support of the measure. So in the Hausdorff metric, under some assumptions on the measure. So there's some regularity assumption, which is called Bernstein-Markov property, without which you cannot prove Hausdorff convergence of the support. Other questions before we embark into infinity? Yes? Mm-hmm.
The picture is, from computer science point of view,
Mm-hmm.
it's very well method for performing clustering.
Yeah.
And how it works when we have more complex shape, maybe to see nested inside.
Yeah. Unfortunately, I did not bring a copy of the book there, but I think you can find part of it also in preprints of Edouard and Jean-Bernard. There is one which is one of the first work they did on that in 2016, which is called the empirical Christoffel Darboux function or kernel, where they studied plenty of different shapes. I encourage you to go there and to including in disconnected shapes and plenty of complicated geometries for competing methods. Yes?
You mentioned that if you have an algebraic set, then you can obtain eventually the equations.
Yes.
Semi-algebraic set from the...
Yeah. Aha. So, yeah, that's a tricky question. So I'm not sure what do you want to approximate a semi-algebraic set? What's the input? What's the output? So the input is the moment matrix, say. What's the output?
Suppose I have like a basic, let's say, basic closed semi-algebraic set.
Yes. Yeah.
I'm taking the
Uniform measure on a basic semi-algebraic set. Okay.
and I'm giving you an arbitrary amount of samples
Yes.
from this measure.
Yep.
And I'm eventually asking
Okay, okay, okay. And what do you expect as an output?
Some inequalities.
You want the generators, which are highly non-unique, right? So do you have assumptions on the generators? You have bounded degree, you know, because it's highly non-unique. So
Yes, let's say they have like some bounded degree. Or they exist some which have like bounded degree.
Then to be totally honest, I'm not sure we can, well, maybe that can be done, but I'm not sure we can really make sense of a problem in the sense that it's well posed and the output is well defined. And yes, Bernard?
So
Yeah.
you will get one polynomial.
Yeah.
Which,
You get one polynomial whose sublevel sets matches with the set. But if your set is semi-algebraic and it's not, say, basic, or it's generated by more than one polynomial, this single polynomial, which is a Christoffel Darboux polynomial, will just approximate the intersection and union of polynomial sublevel sets you started with. But if you really want to enumerate, just knowing how many are they, I have no idea. Or is the set basic or not? I don't know to answer these questions. Just so the output, I'm not sure is well defined. So, you know, yeah, I think it's tricky just to formulate the problem. What's the expected output, and is it reasonable as an output? Yeah. So here we know that the output is just a sublevel set of a single polynomial, which is maybe not the best way you want to approximate a semi-algebraic set, but that's with this tool what you get. Okay, so now let's go to not to outer space. This will be for the end of the talk, but to infinite dimensional spaces. And so what do I mean by that? From finite to infinite dimension. Okay, on the left, I have a point in the plane. On the right, I have a point in the function space. Point in the function space, think of a square integrable function or uniformly bounded function on -1, 1. A point is a function, okay? So if I sample points on the left, I can also sample points on the right. So I just have points in Hilbert space, okay? On the left, I also have a Hilbert space, but here it's finite dimensional, it has dimension 2. On the right, it's infinite dimensional. Okay, there are infinitely many arguments in X. X is a continuum of value between -1, 1. And so now, since we could somehow analyze clouds of points in finite dimensional spaces with the Christoffel Darboux polynomial, there is hope that we can do the same to analyze functions as cloud of points, but in functional spaces. Okay, so the more points, the more functions. Now, on the left, I have a cloud of points. On the right as well, but now it's understood as a cloud of functions. Okay? So now suppose I have a cloud of functions. How can I detect whether another given function belongs, in some approximate sense, to the cloud or not? That's the classification problem we started with. And that's also the anomaly detection problem we started with, because we had, say, a cloud of normal signals coming from a sensor, and all of a sudden we have an abnormal signal. And we want to be able to detect that it's abnormal without an operator, or without a human operator looking at the graph. So that's the idea. Now, in order to do so, we just have to extend the Christoffel Darboux polynomial from finite dimensional Euclidean space to infinite dimensional Hilbert space. So the best suited setup to do that is the separable Hilbert space setup, because it has been designed exactly to be as close as possible to its finite dimensional counterpart. It was designed for that. Okay, so we have a separable real Hilbert space. So separable means that there is a dense countable basis. I can approximate as closely as I want any function in Hilbert space with finitely many functions, finitely many basis elements. And the basis elements I denote EK. It's a countable, infinite number of orthonormal functions with respect to the inner product of the Hilbert space. I denote pi n the projection mapping of the function, infinite dimensional function, to the coefficient space attached to the basis ek. So the coefficients are this inner product of f against ek. That's a real number, and I just take the combination of basis elements. That's a projection. And so by construction, it converges this norm. So any function can be approximated by this projection by letting the degree of the approximation going to infinity. And we have also so-called Parseval inequalities, which relates the L2 norm of the function to the small L2 norm of its coefficients in the basis. Okay? All of that is very standard. So the name of Hilbert is attached to it, so it's early 20th century, but of course, as you know, there is a very strong Polish school in Lwów around Stefan Banach, who set this up in the 30s. So all of that is very, very, very classical. Now we are in infinite dimensional space. We want to construct polynomials. So what are they? What should they look like? What is a polynomial of a function in Hilbert space? Well, what is a polynomial in finite dimension? You take monomials, so they are products of variables, but a variable is what? It's just a coordinate. And so we take just in infinite dimension coordinates, these inner products, and take integer powers and multiply them. That's a monomial. Should be a little bit careful so that this product makes sense. So we'll assume that the degree here is finite. By that, I mean that A will be a sequence of coefficients indexed by K with finitely many non-zero elements. If I allow infinitely many non-zero elements, I should be careful about convergence. And here, if I have finitely many, I don't have to look at that. And the polynomial is just a linear combination of monomials. So in the support of my polynomial, the indices for which coefficients are non-zero, I just sum up monomials and multiply them by real numbers. And you may have understood that already I have, if I do that, another notion of a degree, which is a number of coefficients I use, the number of ek I use to construct my polynomial. This I call the harmonic degree. So the harmonic degree is the maximum value of k here that appear in the monomials that construct my polynomial. And I also have the classical notion of algebraic degree, which is just the sum of the entries of ak, this for all possible a, in the support. So two notions of degree. I use the notation d for the classical algebraic degree. And now n is a number of variables, so number of coefficients. This can go to infinity. This I call the harmonic degree. And in what I will be presenting, the algebraic degree is bounded, always. But the harmonic degree doesn't have to be. Yes?
This goes like monomial by monomial or all variables you use? The harmonic degree.
The harmonic degree is for the whole polynomial. So you take indices in the support of the polynomial and you look at the maximum value of k, which are represented in each index, A. So for a given monomial, so a polynomial is the sum of monomials, and for a given monomial, you construct these objects by taking coefficients of f in the basis ek. And the maximum value of k that you allow in this construction is the harmonic degree of the monomial. And the harmonic degree of the polynomial is just the maximum harmonic degrees of all its monomials. Does it make sense? Or?
All the monomials?
Yes, of all the monomials. Yeah.
But if the first monomial uses like two variables and the second monomial uses different two variables, the harmonic degrees
will be, yes, they will be indexed. So the variables are the inner products of f ek. So they are in this, they have an index. It is k. each variable in index by k, there are infinitely many, potentially. So the largest such index k is the harmonic degree. Yes? It's finite. What is finite is the number of elements in AK which is non-zero. So I will show you an example just on the next slide. So that's an infinite harmonic degree polynomial. The two norm of F. This one. It has algebraic degree 2 and infinite harmonic degree. Why infinite? Because if I want to compute the two norm of a function, I should take the small L2 norm of its coefficients, and there are infinitely many. So the largest value of k, which appears here in the expression, is infinity.
Definition of polynomial, we had that the AKs are in C0.
Yes.
And finitely many non-zero.
So when you do this product, for each monomial, you're not allowed to have infinitely many terms. So here, if you look at the way the product is constructed, it's just quadratic. So the algebraic degree is 2. But you have infinitely many coefficients.
Yeah. For P. But for a polynomial, for a polynomial, it's not possible. It's not
For a polynomial, well, usually what we call a polynomial is something which is finite degree. Here, the finiteness in the algebraic degree. But it may still depend on infinitely many coefficients. Okay? Another way to think about it is to think of a polynomial as a sum of monomials. And a monomial here, I just rewrite this inner product explicitly. And if I call this a moment of my density f respect to the Lebesgue measure, then this polynomial in the Hilbert space can be understood as a polynomial whose variables are moments. This we call the moment polynomial. If there are finitely many moments, then it's a classical polynomial. But here there could be infinitely many.
So sorry, this SPTP, is it a finite set or it can be an infinite set?
The support can be infinite, yeah.
Okay.
But yes, the support, yes. But in each
I think now we...
each element in the support has finitely many coefficients, yes. The sum here can be infinite, like this here. Yeah, yes. So if you're familiar with stochastic processes, they are called Wiener-Chaos polynomials. They may have other names, but well, what could be an issue is that if you have an infinite sum here, if you have infinitely many terms in products here, then there you should be careful because this does not necessarily converge. This depends on the coefficients and so on. But as soon as you make sense of the L2 norm and it's bounded, then it's not formal. It's a genuine function in L2. Yeah. But indeed, if you multiply these objects, you should be careful that they remain in the right Hilbert space. Yes. Yeah. Okay, now we'll speak about compactness. So compactness in infinite dimensions is a little bit more complicated, but not too much. Basically, if I have a subset of a Hilbert space, it will be compact if there is a uniform tail condition. So I take the tail of my expansion. So I project the function on the n first harmonics, and I look at the residual. This should be uniformly bounded. This is the definition. So an example, if you have an ellipsoid, if it's finitely many coefficients, of course it's a compact set. But if you have infinitely many coefficients, this should increase respect to k. So the higher harmonic, the more penalty you have on the coefficient. Another example, famous one, is the so-called Hilbert cube. This is the L2 version, this is the infinity version, and you see that the size of the interval for each coordinate should decay with respect to k. Okay, now, since we could define polynomials and compact sets, we can also define moments of the infinite dimensional object. These are just integrals of monomials against a measure on the compact set of the Hilbert space. So we can construct Borel sigma algebras, and well, this has been done already. We can, as we did in the finite dimensional case, construct a family of finite dimensional vector spaces. Now they're indexed by two indices. Before they were indexed only by D. Now they are indexed by D and N. So it's a doubly parametrized family. And that has a Hilbert space structure with this measure. And I can construct the moment matrix just as I do in the finite dimensional case. Once I do that, I can construct my Christoffel Darboux polynomial. Well, here the terminology I use is kernel, in the sense that what I've presented is just a polynomial of a single argument. It was called X before. It's a diagonal evaluation of a function with two arguments, f and g, which is constructed like that. You see here on the left, you take basis elements of f, on the right of g, and so the diagonal evaluation is the polynomial. So that if you have a spectral decomposition of the moment matrix, you retrieve exactly the same quantities as we had before. These are eigenvalues, and they are inverted to get the Christoffel Darboux polynomial. Mm-hmm.
When you
yes.
So, what you do here, associating to a function a point which is f scalar ek.
Yes. You approximate the function with a finite dimensional vector of coefficients. Yeah.
So you transform this into a point.
Yeah, exactly.
Which is the value.
Yes, yeah, and then you evaluate polynomials at these points. Yes, yeah, exactly. Yeah. Okay, and then we can study this object just as that has been studied in the finite dimensional case. And the good news is that actually all the good properties carry over. So without almost any change. It is not a big surprise because these Hilbert spaces are constructed in a way that mimics as much as possible the finite dimensional case. So these spaces, they are reproducing Hilbert finite dimensional embedded spaces in a reproducing kernel Hilbert space, which means that this linear functional attached to the kernel is reproducing. So it's reproducing means that it will be the Dirac, like the point evaluation, the Dirac measure, but only in the finite dimensional space. And it is continuous. So all of that is very, very classical. That's the direct application of finite dimensional theory. And all the good news is that you have the same average value, the dimension of the finite dimensional truncation. And we have the same dichotomy. Well, I did not mention with formulas the dichotomy property. I just mentioned the concentration inequality. But you have this dichotomy that on the support of the measure, the polynomial will grow polynomially as a function of the degree. And outside the support, it will grow exponentially. Remember these pictures? Inside the support of the measure, the polynomial had moderate growth. As a polynomial, as a function of d, it grows as a polynomial grows, so it grows, but moderately, polynomially. Outside, this growth is exponential, and this can be quantified also in the infinite dimensional case. The only difference, of course, is that we should take the two limits now, or the limit of the respect to maximum of the 2 degrees. Okay, so we have this dichotomy, and so we can use this for detecting signals. And this is the last part of my talk, the experiments we did. Well, so far they are mostly academic experiments, but I will tell you more about what comes next. So, as I said, the goal of this work is to build a detector that can distinguish between good and bad signals. And so the way it is constructed is that we'll construct the detector, this is called training, with a lot of faithful signals, a large number. And the way experimentally these are generated is that I take a nominal signal and I perturb it slightly. And then I will test the detector on a faulty signal, which is constructed as follows. I take the nominal signal, but I perturb it a lot. So here I use degree 4. And 10 coefficients, I think I use Chebyshev polynomial basis. So I approximate a function with its first 10 Chebyshev coefficients. And then I take polynomials of degree 4 of these 10 variate polynomials. Okay? So it means that the underlying dimension of vector space is pretty large. It's 1,000. So the moment matrix has size 1,000 by 1,000. To compute eigenvalue of such a matrix on a computer is routine. It can go to several hundreds of thousands now. So 1,000 is done instantaneously. And as I said, faithful signal, low no noise, faulty signal, high noise. And we use a factor of 2 for the perturbation to distinguish between faulty signals and faithful signals. And so the evaluation is that each signal that I get after I constructed my detector is assigned a single number, which is the value of the Christoffel Darboux polynomial on it. And so if I have a big number, it's an indication that the signal is bad. If I have a small number of the order of the dimension of my vector space, 1,000, I should get good signal. And here is a histogram. These are faithful signals. So these are signals which are around the nominal value but with a small perturbation. And these are faulty signals. Again, the same nominal value but with a perturbation twice as large. And this is the distribution of the values of the Christoffel Darboux polynomial in logarithmic scale. And in the vertical scale, the number of samples of experiments. You see that most of the polynomial concentrate around the value which is actually smaller than the dimension. I'm wondering whether it should not be 10 to the 3 here instead. That's the average value. And you see that the faulty signal take a value, make the polynomial take a value which is much bigger. And if D would increase, then the size of the matrix increases as well. This dichotomy will be even bigger. So if you want to use just the graph of the function, good luck, because the nominal function is in black. The cloud of faithful functions is in blue. And the faulty ones are in red. And just looking at the graph, it's not easy to detect that there are faulty signals. But if you look at the vector of Chebyshev coefficients of those, you as point in R10, you see the dichotomy. Okay? And the last graph, which is so-called area under the curve graph, which is for a given threshold of the Christoffel Darboux polynomial. So I could use the average value, but I can change the threshold, use different sublevel sets. and look at the number of positive, of true positives and false positives. And so ideally, I should have something here in the sense that I don't have false positives and all my points are true positives. And each point on the curve is for a given threshold. And you see that the optimal threshold is somewhere here. It's related to the average value of the polynomial. But most of the graph of the ratio between false and true positive is in the up left corner. So if my detector would be random, this curve would be just the diagonal. No distinction between true or false. Okay? And that's the end of my talk. A few concluding comments. Much remains to be done in terms of the practical application of this on telemetry of satellites. We have a PhD thesis, which is just starting now, which is fully funded by the CNES Space Agency. The PhD student has been identified. He's a former intern of CNES, Florian Grivet, and he will work on that. And it will be co-supervised by Jean Bernard and Luis Trave Massues, who is an expert in diagnosis and fault detection at my lab, and Lionel Vintena, who is an engineer at CNES. And also, even more recently, actually, we had email exchanges yesterday night. Colleagues from robotics in Paris, Frédéric Dungen and Louis Nel, have been playing with these kernels to detect anomalous trajectories in robots. So I don't have material consolidated enough to be presented today, but hopefully more will be done along this direction, and we'll welcome them in mid-October in Toulouse. We'll be working on that together. Okay? Thank you for your attention.